last time we reviewed the semiconductor and the structure of pure semiconductor like silicon, germanium. Yes.
Jordan, when we met, said that it might be coming a bit later.
Okay.
Because it's just back from training.
No problem. That's why I like to record the lecture. I know I didn't post anyone yet, except only the PDF, because we didn't start in serious stuff from now. I mean, I'm recording now, so we'll not have problem with that. So and we said that the pure silicon have 3 electrons. No, didn't have 3 electrons, right? Pure silicon. Because we have 4 electrons in the outer level. We call it covalent band. And so every 4 silicon atoms, they combine together to complete the outer orbit 8 electrons. But we don't have any carrier. When we say carrier, it means free electrons or holes. Except only few. And these few carriers of few electrons, they happen by thermal effect, right? If you solve the 2 pages multiple choice question, I advise to review again. I posted the model answers, so review again to review the concept of semiconductor physics. So there is nothing there in pure silicon or germanium except only few electrons because of the effect of temperature. So they get some energy and they can escape, but very few. But we found out that we can do N-type and P-type by adding impurities to the semiconductor. We get different material that doesn't have 4 electrons. For example, N-type, we add atoms that have 5 electrons outside. So if every 4 silicon, they are participating, so everyone will have like 8 complete. But if there is one of the silicon, not silicon, it's just you add the impurity pentavalent atom that has 5 electrons, so there will be extra because it's complete 8. So where is this 5th? Because it should be 4, 4, 4, 4, and then there has one extra. It has 5. So that extra electron. This electron will be the free electron. So this semiconductor material will be extrinsic. It means it has impurities, and N-type, it means you will have free electron. And we call it N-type. As you see, that's the free electron that we're going to have, extra. But if you don't add impurities, the material will be pure, the silicon, and 4, 4, 4, everything will be completed 8 around its outer level, and you don't have any extra free electron or holes. Okay. What about if we add impurities that does not have 4, it doesn't have 5, but has 3. So we'll be missing one place. One of the electron is missing here. And when there is a missing electron, what we call this one? Hole. It's just empty spot waiting for the electrons. Some people, they try to say it's a positive charge. Well, let me see if anybody here waiting in the waiting room. Okay, we are here. All right. So we'll go back here, the N-type. We said we have 3 electrons, and we're going to use this representation, N-type. 3 electrons, it's negative. As you see, this negative sign, that's the free electrons in the material. What is this circle and has positive? This is the atom of the impurity itself. That tells us. So just we when you look at this one, the positive and circle, this is the atom of the impurity that has 5 electrons, but we show only the free electron, the extra one. For B type, as we explain, you are going to have hole here from the atom that added that has only 3 electrons in the outer level. And when we represent the P type, this the holes we said that we can consider it as positive charge. It's represented by positive, and the circle has negative. This is the atom of the impurity, the one that has 3 electrons. Yes.
Jordan is trying to get
Well, I tried to see if anybody. I don't see any message here. Participant here. I don't see anybody in the waiting room. Oh, okay. There's one here. Yes, yes. All right. All right. You're very welcome. I thank you. And that's the B type. So when you use this representation, we understand what does it mean. Again, just to not to forget, this N type, the circle has positive that represent the impurities and has negative outside is the electron. The free electrons has free electrons. The free electrons negative sign. And the rest of it will be the atom of the impurity. For B type, you will have holes represent as positive charge and the atom of the impurity negative sign inside the circle. So that's P type, that's N type. You got to remember something. Let me just ask you. If I ask you about B type, choose one of the answers. B type can be considered as positive ion, negative ion, neutral. Choose one and tell me why. B type. Can you consider B type positive ion, negative ion, or neutral? And why?
What's the question?
Okay, the question is, let's pick something like P type. This P type, that semiconductor, we add impurities, as you know, and we have holes here. So can we consider P type positive ion or negative ion or neutral?
Positive.
Positive, okay, I want to hear. Yes, because it's missing electron. All right. Do I have other answer? That could be like multiple choice question. That shows, like we did last time. All right, I want to hear from everybody. That okay, everybody had. You guys are 4 people, and also people in the Zoom. They can tell me if they have an answer. Everybody got to tell me answer. If you agree with your friend, okay, say it's positive charge. Well, agree about it. Okay, what do you think? Positive, negative, neutral? Positive, okay.
Yeah, I think
Positive also. All right? Same. Let us see the people that were involved.
I would like to apologize for bad mic quality. I've been told it's
No
very
problem.
quiet.
We can hear you well. Did you hear the question that just asked?
No, I didn't.
Okay, let me state the answer, the question again. Where we are saying here in B type, as we explained last time, it's a semiconductor material like silicon.
Okay.
And then we add impurities that has 3 electrons in the outer level. So as you see here, the bond here, they are sharing the electrons. Imagine if this one, this impurity, if it was this is silicon. Imagine this blue 1B, that's the impurity. If it was silicon, you will have 4 electrons, and then everything is complete in the outer level, 8 electrons, 8. But now, because we have this impurities, the B boron element, it has only 3 electrons, so it's missing here electron, which is going to be a hole. All right.
Yeah.
So the question is, in this structure of B type, can we consider this B type positive ion, negative ion, or neutral? The answer that we got here, just tell you the answer here, the class, they said they agree about it's a positive ion. So what do you think?
I believe it would be positive because it's
Okay. All right. Thank you. Let me now explain something. The positive ion or negative ion in neutral was different. The atom, we explained before, it's neutral. The number of protons equal the number of electrons, right?
yeah.
So,
but it's it's
right?
still 4. Never mind. Yes.
So we added, yes, we added impurities, but even this impurities is an atom, neutral by itself. The all silicon, let's say that we have 1, 2, 3, 4, we have 4 silicon atoms. They have 14 electrons, 14 protons, so it's 0 charge. When we add this impurity, boron, it has in the outer level, yes, it has 3, but still the number of electrons in this impurity equal the number of protons. It's protons, neutral. Nothing is the whole structure. Yes, we are saying there is a hole, there is a place waiting for free electrons to come in, but the total number of electrons in this structure equal the total number of protons in this structure, in this structure. So actually it's neutral. Yeah, there is a hole. Or even n-type. N-type, it has free electrons. Doesn't mean has free electrons. I can call it negative ion. Why? Because the total number of electrons in this structure equal the total number of protons. So no ion.
Okay.
Right? Yeah. When happen ion, if you have atom and has, let's say it has like +5 and you have your 5 electron, and there is one leave the atom completely, then we say that. But if the atom is still in the if the electron is still in the atom, like in one orbit, instead of conduction, it's the covalent, but it's still there in the atom, so it's not ion. So n-type and b-type, they're not ion, they are neutral. But all what we can say, n-type has 3 electrons that they can move. That's all. And b-type has 3 hole waiting for electrons to occupy it.
Yes.
So how we'll do and that's how we represent B and n-type. Now, if you put together B and N, so we'll have a structure called BN junction. And we call this diode, and I'll say why now. Actually, in manufacture, how they do, they get the silicon and then inject the right side with impurities that has 5 electrons, and the left side with the one who had 3 electrons, different impurities. Then you got B and N in the same place. And then there is the boundary here between the P and N that we call it the junction. That's why they would call it junction diode. Call it junction diode. Yes.
Interesting.
Yeah, it is. Yeah, it is. I'm sorry that I'm explaining physics because we got to understand it, but once we go to the circuit, so I understand how free electrons are moving in. So when you do that, all right, that's the diode. And by the way, it's very important structure. It's not BN junction only use a diode. That's actually, if you like to read about BV panel that used for solar energy, it's from the same material. But I'm not going through it. It's very similar. If you understand that, you can understand the solar panel, BV panel. So let's say now how they can make this structure perform function. I just remind you what we have here, BN together. All right. Can you tell me what is P? That's P. How do I know this is P? Because it has positive represent the holes, and the circle negative, it represents the atom of the impurity, and this one N. Type, because I have 3 electrons, which is negative sign here, right? But as you see, everything is neutral. Now, let's see what's happened, this interesting thing. What happened exactly? That the free electrons, they are just free to move anywhere. So let me just take you to this picture here. So what happened to this negative, this electron and free? Free means in the conduction band. It will go cross the boundary. All right. It will cross the boundary because this free electrons. Then they will have like a repulsion. They just will go cross far from it. When it cross the boundary, what will happen? This electron. Remember, this is not positive charge. This represents hole. So when the electron move cross the boundary, what we call this, the junction, right? When it crosses the boundary, it will lose some energy. It moves, lose some energy, becomes weak. Then it will go to the hole. And once it go to the hole, become neutral. The hole vanish. The free electron vanish. And this will happen for many electrons. So that's one I just show you here in this diagram. It's missing negative and missing positive. It means that this electron, when you go and fill the hole, it's like a recombination process happened there. So you missed electron there, you missed it. And this will continue. And this will continue. As you see here, the all negative sign, they are not there. And the all positive sign are not there. What does it mean? It means the free electrons next to the boundary and the holes next to the boundary disappear. Because the electrons, the holes doesn't move heavy, right? Just the electrons cross, and then just every electron go and fall down in the hole. Then, so what happened? This region that I sketched here, I didn't put anything. Why? Because I'm focused on the carrier. What does it mean, carrier? Carrier, free electrons or holes. So this region next to the boundary doesn't have free electrons, neither holes. So there is no any charge of it, just nothing. No free electrons, no carrier. Then I make it like in between region, but of course it has atoms because when, as you see here, if you look at it, there are things there. But I'm talking about the free. Means this region does not have free electrons or holes. We call this depletion layer. We call it depletion layer. Observe here. What do you have here? Remember, I said in the beginning it was neutral. And this missed now electron. Missed electron, right? The number of electrons less than the number of protons. So you can call this positive, can call it positive ion, positive charge. Yes, I agree with you now. But before it was neutral, missed the electron, it's a positive. What about that? Negative charge, yes, because the holes are filled. So you have across the boundary of the BN junction, you have this region, the depletion region does not have free electrons, doesn't have holes, doesn't have carry, but it has charge, positive and negative charge. Because you have a positive charge, a negative charge, and still this material like insulator, but you have positive and negative that work like a capacitor. You know capacitor? The capacitor, you have two plates, one has positive charge and one has negative charge. Then you will have electric field, right? You will have electric field. Positive charge, negative charge, insulation, that's a capacitor. We have electric field. Do you understand what does it mean, electric field? When you make the lines like that, the arrow going like that, you got to understand. You cannot see electric field, you cannot see the magnetic field physically, but you can see their effect. The electric field, these lines, that's visual, but you can see it if you put positive charge, small positive charge, you'll find it's going in the same direction of electric field. That's the meaning of the electric field. So if you put a positive charge, very small. You'll find how it moves in the direction of electric field. What about if you have electron? If you have electron, it should go in this direction, the opposite, right? So what happens when you have electric field here? It only allows positive charge to move from right to left. But electrons, what happens to electrons? As I told you, if you have, this is electron and this is positive charge. The positive charge moving from right to left. The electron, if you have put electron here, it will move from left to right. So the electrons here will not be able to cross the boundary anymore. Why? Because this electric field in the boundary area or the depletion layer prevent any electrons to cross it. Because it's opposite, the electric field in this direction, only move the positive direction in this direction. But you have electron here, it will not move it. So it prevents it. It will not be able.
So once it crosses over, it can't go back?
Whoever crossed, recombine with the hole and make the charge. But I'm talking about the rest of the electrons. After the electric field here built, it becomes like a barrier. No more electrons can cross. But before they were free because there was no electric field built yet. They were crossing and recombining, and then in the end, the electric field established by this in the depletion layer, it will be like a barrier that nothing can jump because it's opposite to it.
Right. Okay.
Yeah, and that's amazing. You know what? Because that's it. No more electrons moving, and this is like a barrier, like a mountain. Nobody can jump anymore. And now people think, okay, the scientists, how can we take advantage of this one? Said, okay, if we apply voltage or electric field to force this to go, maybe we can. So now if you put a battery like that, and this battery that's the positive here connected to the B, and the negative connected to the N. So what happened now? Well, let's just explain it little by little. We said that this will make electric field which equivalent to voltage, small voltage. Why I'm saying that? I told you it's like a capacitor, and you got in circuit the capacitor. How the capacitor work? You get, that's the capacitor, you connect it to, let's say if you connect it like that, so the positive, this will be, plate will be charged by a positive charge, and this is negative charge, and then you have the electric field, and this is the capacitor. So already you have electric field. So what does it mean? It means that this is equivalent to some kind of voltage. Let me call it VT, but small. In silicon, you can see it's 0.7 voltage. It's equivalent to 0.7 voltage. So when you come here and you connect this one, remember that you have voltage here. That just make it. It's like exactly. It looks like that. 0.7 volt. So if you put battery like that, still zero, nothing happens. Still this barrier, VT barrier, prevent electrons. Then you start to increase this voltage. 0.1, 0.2, 0.3, still VT bigger. 0.7, you increase it but to 0.8, so the voltage of the supply is bigger than the VT, the barrier voltage. Then it overcomes this electric field and can now allow electron to go. We call this forward bias. Forward bias. Forward bias, when you connect P to the positive polarity of the voltage source and N connected to negative polarity of a voltage source. That will, and that's condition number one. Connect positive polarity of the voltage source to B and negative polarity of the voltage source to N. That's condition number one. Condition number two, the magnitude of this voltage should be bigger than the barrier voltage or VT, the voltage at the depletion layer, across the depletion layer. Why? To overcome the electric field that built there. Yes.
So even though there should naturally be a depletion layer there, you're using the voltage to force.
To overcome it, yes. To allow electron go flow and towards the positive. Yeah. So the electron will be flowing here because you want to go to the positive and leave behind holes. And the electrons in the battery will be flowing here to, you see, to replace what's missing. So you will have a complete circuit, and then the current will go in PN junction. But that's great. They thought about how to make the electrons flow and electric current go through that. If they want to stop it, what should they do? How do you stop it, do you think? If I want to stop the flow of the electrons, if I want to stop the current to flow in this junction, what should you do, you think? It makes sense. Just if you look at what we did, you can guess. Decrease the voltage, and then if you decrease the voltage till you reach the exactly, but you want to make it harder even for any small current to pass. So what you'll do, flip the polarity of the voltage. Because if now you connect the negative to B and the positive to N, what will happen now? All electrons here, they want to go towards the positive, right? So these electrons will going in this direction, leaving more positive ion here, and this one will be replaced by the electrons. So the depletion layer is increasing. Instead of was like this size, small size, in the beginning it was just this size, and when I reverse it, so the electrons here will go in this direction. So leaving this positive ion, you are increasing the positive charge on the right and increasing the charge on the left, increasing the electric field, increasing this voltage barrier. It will make it harder and harder for any electron to cross. We call this reverse bias. So reverse bias, you connect P to the negative polarity of the voltage and N to the positive polarity of the voltage, and it doesn't matter the magnitude of the reverse bias because it's enough to do this job. And actually, this resistance I have here doesn't have any value because the current is be zero. But in this forward bias, it's important to have resistance. Why? To limit the current. Because if you didn't put resistance, the current will go to infinity. So you put resistance in this forward bias, it's important to limit the value of the current flowing in the circuit. This is diode. Here you go, this is diode. That's called rectifier. What the function happened now, rectifier. We made this silicon that has impurities, allow current to flow in one direction and stop if you reversed. So what does it mean? Imagine now, so what we did to now, we have, let me just make it simple here, Pn and Pn. If you connect P to the positive, let's have resistance here. That we call it forward bias, right? And if you connect B to the negative, we call it reverse bias. Here, the current will flow in the circuit. And here, current is zero. Amazing. So what is the advantage? Let me tell you the advantage here. Let me just tell you, if you have a diode like that, that's P and that's N. And I'm going to connect it to AC. AC has two cycles, positive and negative, right? So when you have the positive cycle, what will happen to this diode? Will conduct, right? So what you get here, you get the positive cycle. When you have the negative side, it's open, nothing will go. If you have another positive cycle like that, so it will allow only the positive cycle to pass and the negative side will be zero because reverse bias. It will forward bias when it's positive, reverse bias when it's negative, so only allow the positive. So I converted the AC into DC. Is it DC? Yes, even it looks like not straight line. Straight line does not mean DC, means regulated DC. This is not regulated. And I can show you that I can make this regulated. If just you add capacitor, it will just smooth down. That's all. So I converted AC to DC. That's why they call the diode rectifier. You hear this word a lot, rectifier, diode. You call it diode, it means two poles. It has two poles. It has two poles, P and N. That's what we call diode. But they call it rectifier because it rectifies the AC to the DC.
And that diagram you drew where it's positive and negative zero, that's for forward or reverse bias?
Oh, you see, when you look at this AC, you got two signal, right? If you take the first cycle, what looks like? It looks like you have a diode like that, and then you have positive. Means positive, right? So it will be on. But when you have it, the negative cycle, when it comes, what's mean negative cycle? Let's say that's negative 10 and this is positive 10. What does it mean? It means that you have a battery, reverse bias, and it's changed from 0 to negative 10. 0, negative 1, negative 2, negative 10, negative 9. It's always, all the time negative. So always reverse bias. And once reverse bias, you represent the diode as an open switch. When it's forward bias, in this case, diode behaves like closed switch. Switch is on.
Forward bias is always positive, reverse bias is...
Forward bias, no, you cannot say just positive. It also has zero positive. No. Forward bias, positive connected to B. Positive connected to B. Or you can say B is more positive than N. Reverse, the voltage applied in B will be, no, N will be more positive than. So forward bias, when you apply voltage, positive with B more than N. Reverse bias when you flip it. So remember, when you connect P to the positive, that will be the forward. B to the negative will be the reverse. And it will behave like a switch, open switch. And that's what we call it rectifier. As I explained to you that in reverse bias, of course, what happened that increase the depletion layer, it doesn't allow to grow. Of course, even when you, here it's reverse bias, by the way. But we can feel some currents flowing, very small amount of current. Ideally speaking, zero, but it's not zero. When we measure, find just very, very small, you can see microamp. Like if you have forward bias in circuit, you can feel that you can pass like 10 milliamp. And then when you make it reverse, it will be zero, ideally. Well, you can feel like you have 10 microamp. Very, very small, yeah. But the question is, why? Why this small current come from? Come from where? Remember, current, it's always come from free electrons. Or carrier, you can say. So if it's reverse bias, and weak signal should be zero, and there is a barrier, so what that energy that get to these electrons to, not all of it, of course, very, very few, but how they got this energy, from where?
Would it be from the depletion layer?
Well, depletion layer doesn't have energy, it's a barrier. It's like, it's a mountain. Imagine this barrier like a mountain or high place, and you have electrons, and these electrons you cannot jump. But there is some hyper electrons that they can jump, but very few, very few. So they got the energy from where? Because the rest of the electrons didn't have energy, but these guys, they got just some energy. It's the same when it was silicon before you put the impurities. It's the thermal effect, because of thermal effect. And if you review the multiple choice, the question last time, you will know that the minority, called minority current, it's because of thermal, of the temperature. It depends on the location. It's close to this high temperature, or by the collision, some they lost, they didn't collide. There are many factors affect that these electrons still keep and gain thermal energy and jump. Because when the electrons move, even the free electrons, they have energy, but when they move, they lose some, and they collide, they lose some. But some, they don't, they are lucky, they don't, it depends on the probability, they don't collide. So this, the minority current, even in reverse bias, it happens because of the thermal effect. And when you increase the reverse bias, and this thermal current can, it can happen something. If you increase really the voltage and you exceed the limit of the diode, you can break, what happened, breakdown will happen. And this minority current will increase in flowing. The breakdown will happen and will increase, and then you'll find that the current going in the reverse direction, and we don't want this to happen. This means the diode is not working, and it's the breakdown happen to the diode. So when we increase the reverse voltage, we have limit, and this and these limits are given by the manufacturer. They give the, even there is a maximum current given by the manufacturer. We should not exceed it, because if we exceed it, even it's a forward bias, but it has limit. What has limit? Because you depend on the electrons, the free electron inside this silicon, inside the semiconductor. When you increase the voltage till you get all the electrons out from the conduction band, because free electron is conduction band. If you increase and all electrons are gone, so now we are getting electrons from another level, giving energy. They're supposed not to move, and then you break them, the atom and the structure completely destroyed, and then you will have like a piece of wire. Because that's true. When you increase the voltage forward bias, it's good, but increase to infinity. If you have like 1,000 free electrons and you're increasing the voltage, the forward bias, then you make 100 moving, 200, 250, 300, 1,000 move. When you increase, what happened? The all free electrons are out. So now you're getting the guys that they are laying down, attached to the ground, and then you break it. No, doesn't work. So it's broken, because these guys on the ground level should not move, because the structure completely will be destroyed. So we have to make sure that we never exceed the maximum current, and we never exceed the reverse, or we should not reach in the reverse bias the breakdown voltage. And I'm going to show the curve so you can understand what's happening here. That's the diode. Now let's go to the circuit. This is the way that the diode log. That's P, that's N, and that's how you can see the diode symbol. Like an arrow like that, and this line, always remember this line in the head of the arrow, that's the N. All right, because we're going to use this all the time. We're using PN just to understand the physics of the diode. And there are many shapes of diode. There are diode like maybe this one that you will see a lot in the lab. And by the way, they call this anode, and this is cathode. And you see it in the lab. There is a ring here. You see, if you just make it like, let me make it bigger here. You see this ring here. That means that here you have N, and here you have B. The ring and small space in the front of it, that's N, and the rest is B. That's how we do it. And you can test it by the ohmmeter, and I'll show you how. But they call this anode and cathode. It has, of course, reason, because before they do the semiconductor diode, there was something called vacuum tube. I don't know if anybody saw vacuum tube. That's in the history, the old days. I saw it. Before in this semiconductor device, before they have vacuum tubes, you have like a light bulb like that, and had like a grid, and they had like a filament that they heat it, and the electrons emit and go through it. It's the same process, but real electrons emitting, and you can see it like a light bulb. I saw this TV, huge. And in the back of the TV, huge, because it has tubes and has this big coil that make high voltage, because to free electrons, you get to have high voltage to give it energy, a big electric magnetic field. And you see the light. That's why I remember my grandfather when he has TV. You turn it on and you wait just for 5 minutes to get everything get hot and the clothes start to emit, and then you wait. Even if it's cold, in the winter we used to go just next to TV, just with our hand, to get warm, So they call it anode and cathode before, and they still keep this name, and that's okay. So that's the normal diode you can see in the lab, and this is another one. There'll be different power rating. Yes, there are power rating. There are milliwatt and there are watt, and there are 10 watt, 100 watt, and every time that's bigger. And I work with this diode because I'm power engineering. So this is the diode. It looks like a nut, that there are small diode, small signal, operate with milliamp, and there are diode used in rectifier circuit. It can operate with 1, 2, 3, 10 amp. And I work with diode that work with 100 amp. So you got the old, but this big one, the top call it power diode, used in with high voltage and high current rating. So how you sketch the circuit? The circuit, that's the diode. Remember, this is V and N, and this is what's positive and negative. That's to find the voltage across the diode. We measure both the positive here. That's the red of the voltmeter to measure the voltage. So that's the positive, and there's the negative. Always when you say the voltage is equal 0.7, 0.8 means that 0.7 greater than this one. All right, that's the positive, negative. Resistance and VS, of course, is forward bias. So how that's be connected. Now let's look at the circuit. The characteristic or the diode curve. How we do this? This can be done in the lab too. We'll get the diode, and just because maybe you don't remember yet, I'll write the PN just to remember. And you can get like voltage, that's forward bias, and you can get a resistance. What you want to do, you want to find the characteristic of the diode, the relationship between the voltage across the diode and the current through the diode. That's the characteristic of the diode. So the x-axis VD, it means the voltage across the diode, and ID, the current through the diode. As we said before, this voltage, let's say it's the supply voltage is kind of variable, like power supply in the lab that you operate. I start with 0. So what's the current? When the voltage supply is equal 0. So what do you expect the current in the diode? 0. Why? Okay. The voltage become now 0.1. What's the current?
First turn on, well, close to 0, right?
0.1, 0.2. All right. Huh? So what's the current? 0. Why?
Still below the barrier voltage.
Exactly. Because we said that has to exceed the barrier voltage. There is barrier voltage for everyone. Okay, so it has to exceed the forward voltage, which in this case 0.7 volt. So if you increase, you got to reach. That's why I'm going to make. You see, listen up. 0, 0, 0. It has to reach 0.7. Less than 0.7, no conduction. The diode is off. But once you reach 0.7 and you increase to 0.75, the current increase rapidly. Look at the slope of this straight line. It's not, you see, let me show you. It's 0, you increase, still everything is 0. That's the voltage across the diode, that's the current to the diode. But the current, once you reach 0.7, it will start to conduct. But it doesn't conduct like that. It's not moving or increasing slowly. No. It is increasing like that, almost vertical. Almost vertical. Like, ideally, we are going to represent as a vertical lines like the resistance is almost equal 0. And actually, the resistance is so small, 0.1 ohm, 0.2 ohm, so small. That's why when in the lab, when I was a student, I was just astonished. I just increased it 0.8, and then the current was 0, then jump. So I thought I did something wrong. I asked him, no, this is the diode. So when we increase the voltage, it's very slight. And remember, as I told you, there is a limit. Like it's increasing, it's not vertical, but increasing slowly. It should not exceed the limit. We call this I max, the forward maximum current. We should not exceed. And the corresponding voltage will be called V max. So now we call this the forward region. What does it mean, forward region? It means that the voltage applied to the diode in this region, it was forward biased. The positive polarity of the voltage was connected to P, like in here, and the negative polarity of the power supply connected to N. So you are operating in this region, forward region, positive VD, positive ID. Let's now go to the reverse. What you'll do to do the reverse, you remove the battery to test the circuit, and you are going now to connect it in the reverse bias, negative to the positive, positive, and start from zero also. Make it the power supply. Flip the lens of the power supply and start from zero, increasing the negative. Observe there is nothing. The current is nothing. You can say less than micro. And but of course, as I told you, it'd be like something micro amp. And if you go to the make projection, that's the current. You see, very small, completely different. The forward bias, you see how it jumped quickly, but the current is not increasing at all, almost constant. That's the thermal current, minority carrier. So, but once you reach the breakdown that I told you about it, the current will increase rapidly in the reverse direction, which is not required. Once you read, so the manufacturers give you this value, the breakdown voltage, V, sometimes breakdown, right, like that, should not be exceeded. This is the reverse voltage applied to the diode. After this value, the diode is like a piece of wire, current increasing, but increasing in the reverse direction. All right. Amazingly, the engineer, they never give up. This property said they found is very important, and they can use it in some application. And I'm not going to talk about it today, of course, but just I'd like to remind you, remember this phenomena that we don't need it. It's not good in our application as rectifier. They use it to make Zener diode. And Zener diode, they use it to regulate the voltage, to make some voltage constant. It's not our subject today. But as a diode rectifier, we don't work in the reverse direction. We don't work in the reverse region. No, we work on the forward region.
Quick question.
Yes, go ahead.
So when you're in the forward region, like when you first start, say your voltage is zero.
Yeah.
Your current's going to be zero.
Yeah, of course.
So you don't have that microcurrent happening. It only happens in the.
Oh, okay. I see what you mean. Yes, you can say it's still there. Yes, the minority always there. Because the thermal, some electrons just get the energy. Yes, of course, yeah. But you got to know the difference. The minority carrier here moving in the forward direction from B to N, and the other one moving from N to B. So it's like the other direction, but they are there because of thermal effect. Yes. But because of forward region, as you see, the current increase rapidly. Once you reach the knee of the curve, we call it the knee of the curve, that when you exceed the 0.7, forget about the thermal current, because you are talking about the majority. They are moving, many free electrons, they are moving a lot. So that's the characteristic, and we are going to do something interesting. First, we are going to represent diodes by ideal switch. What do I mean ideal switch? Means that you put positive voltage, switch is on. You put negative voltage, switch is off. So the current is either going everywhere or off, zero. We don't talk about thermal current or anything like that. We don't talk even about the 0.7 volt, because as engineer, when you do the first calculation, you don't have to be precise about everything. You just want to get an idea. So say I don't have 0.7, 0. And then you apply your voltage and you make your calculation. It will give you a good estimation, by the way. And you will feel it now with your calculation. So how you represent ideal diode by switch? This switch is open when it happen like that. When you put negative voltage here and positive here. And when it's on, when you make it forward bias, when you put positive here and negative here. So when it's on, the resistance is equal 0, short circuit. So R is equal 0. So if you divide V by 0, what you get? Infinity, right? That's what you have. Current is infinity. Even at once you cross the 0. When it's reversed, it's open. Current is 0. This represents current is 0. Because if you go to the current, that's the current here, the current I is equal 0. All right. So ideally speaking, forward bias, when the voltage across the diode greater than 0, current will flow. If the voltage across the diode is less than 0, current is 0. That's all. Let's see how we can apply this to analyze circuit has diode. And most of the engineers, when they do the analysis, before they go to make simulation and make the complicated modeling, just to use this one. It will give them idea. Because when you use this estimation, maybe you'll calculate the current you find is equal 20 amp, for example. And then if you make it the exact, you'll find it's equal 19.7. So what? But of course, important some application. What I'm saying, that's good for give you idea what you're going to have. All right. Here you go. Now we'll go for our business now. We want to do this to analyze in a circuit. Let's take it to our node to solve it. Oops. Oh. Okay. Here you go. So how you solve circuit like that? To solve circuit like that, always simplify it to one source and resistor. And then you connect your diode. Because that's what when you look at it, let me just mark on it. What's required in this? You need to find the current in the load and the voltage across the load. So this is your load RL. According to that. So this is your load. Your load is diode connected to the resistor. The rest of the circuit here, it's better to be simple. How you make it simple? You can. I will ask a question. Can you represent? I will just make a different color, so I can. Can you represent this part in red by voltage source and resistor? The one circuit by red color. Can you simplify it by a simple voltage source and resistor in series? Yes or no?
I
No,
suspect that you can, but I don't know how.
Okay, that's right. Yes, we can. Did you have EL 150? Yes, DCSE. Did you study the theories to analyze circuits and simplify it and find the equivalent circuit?
I had it, but I had a hard time with it. So.
Oh, okay. That's important. And the theory I'm going to mention now is really important in all electrical engineering circuits. Always we simplify any complicated circuit here or in the lab by Thevenin equivalent. Because Thevenin equivalent can, you see, if you have a board, let me just give you an example. And I did that in the lab. Let's say that you have board and you got two terminals. And you want to connect your load. But before you connect this load, maybe you connect it to the board and then you get like high current or high voltage, whatever, destroy your load. That's your load. And you don't know many things inside here. So what you'll do, if you can represent this board or this complicated circuit, if you can represent it by resistance and voltage source, life will be easy. That's R Thevenin, that's Z Thevenin. So you represent the whole board. Maybe it's complicated. The whole board by voltage source connected in series with the resistor. Then it will be easy to make analysis. You connect the resistor here of the load, and then you say the voltage divided by the sum of the resistor, you get the current, and then you see if this current reasonable for your load or not. If you do this calculation, if it's reasonable, connect it to the board. That's all.
So you basically would, in this scenario, you would add up both of those resistors together.
Exactly. Because if you want to find the total current now, the load current in this circuit, you see it will say IL is equal V Thevenin. You just calculate divided by R Thevenin plus R load. Because they are connected in series. R Thevenin, R load, they are series. So you divide the voltage by the total resistance, you get the total current, which is really nice. So it's very important, the theorem that you studied in EL 150, especially there are certain theorems that they are very valuable in certain application, many applications, like Thevenin in all application. When you want to simplify circuit, complicated, just do it. You have superposition. If you have different, if you are dealing with frequencies and filter, and you got the source has different frequency, that's superposition. You can escape. So there are important theorem that you should be familiar with it. Now, I think Thevenin, this circuit that circled by red color, I will try to find its equivalent. Let me just sketch it here. What do you have inside this red circuit? You have a resistor. It's equal to 6 kilo ohm. And you have
another resistor equal to 9
exactly
kilo ohms.
That's right. It's equal to 9 kilo ohm. And these are the terminal, and you have a voltage source.
Yes.
Which is equal to
96 volts.
Yeah, it looks like. Let me just. What is that? 96.
36. 96?
Yeah, it looks like. Yeah, you are right. Yeah, 36. Yes, 36 volts. That's right. So, and let's just call this terminal AB. If you found the equivalent circuit. Oh, by the way, no, just that's your load. This is RL equal 1 kilo ohm, and this is diode. And we are going to represent ideal. It's like switch on and off. So I want to simplify the one to the left. I wish to find the equivalent like that: one voltage source and one resistor. I wish.
So
and yes,
it looks like a sorry.
Yeah.
I think it's like it's in, if you treat it like it's in series with
which one? 6 and 9. 6 and 9.
6 and 9.
Okay. To do that, first we kill the source. Remember the source. Kill the source. How you kill the source? It depends. If it's voltage source, you kill it. It means make it zero. What does mean voltage equal 0? Short circuit. So I will sketch the same circuit again here. 6 kilo ohm, 9 kilo ohm, and I supposedly I have here voltage. I will kill it by making short circuit. Short circuit. This is gone. So I replace the voltage source by a wire. What about if it's current source? You remove it, be open circuit. Because I0, it means open circuit, but V0, it means short circuit. And now I want to find the equivalent circuit. Now I think you can find the right answer if I ask you, what is the equivalent resistance when you look from this one? What is the equivalent resistance? Anybody has idea how you find the equivalent resistance?
Is it 15 kilo ohms?
No, you cannot say that, because I'll tell you why. Because if you assume the current going in, if you assume there is a current going here, and this junction would happen, it will split. And when current split, it means parallel.
Okay, so, all right, that's got a little bit more complicated. I remember how to do
So,
parallel, but I can't.
because I mean, I say, okay, I said that's your terminal AB. I said, if I have current coming from here, what happened to the current? The current will split, will go, one go through 6, one go through 9. So since the current, not the same current going through 6 and 9 kilo ohm, it means they are not connected in series. So they are parallel. What is the condition for series? The same current is flowing through both resistors, right? To be serious. But this one split means everyone has its own current. So be parallel. So be 6 times 9 divided by the sum will be 6 times 9 divided by 15. So let's simplify. That's easy. We don't need calculator. So by 3 is 3, by 3 is 5, right? So you have 18 divided by 5 ohm. Okay, that's our calculator. 18 divided by 5, 3.6. So we have 3.6 ohm. Now, I found this value of the R equivalent. That's equal 3.6. That's kilo ohm. I'm sorry. That's kilo ohm. Because everything was in kilo ohm.
Yep.
That's yes.
Yep. Everything was in kilo ohms.
Yeah. So now I need to find the voltage. That's my second step. I go back to the circuit. To the circuit here, how you do that? Let me sketch again 6 and 9 and 36. It's better to have always a fresh one. So I will have 6 or kilo, 9. That's the terminal AB where I put the load, and I have 36 voltage. So I want to find the voltage between AB. Well, this is open circuit, so if the current going here, nothing will go out, right? Now I'm applying the voltage. I have source.
If you were to apply the voltage like that, then that would mean that nothing would go down A or B except for...
Exactly. That's right. Because it's open circuit. I don't want anybody confused. When you find R Thevenin, to find the resistance, you got to imagine that you have current source here, because a current has to go through the circuit. You kill the source here, nothing here. So you put source here, just to imagine if the current going here, how it would go. But here you have voltage source, so you are not going to add another source. So this source will produce current going through the circuit. So in this case, 6 and 9, they are series or parallel? Series. How can you find the voltage across AB?
Do you have to pretend that there is it's not open? You have to pretend that it's a...
No, it's open. It's open. Even, I mean, you can move completely, remove this one and only have, it's open. Just I put this wire because I want to find AB. So I just got 2 wires to put the voltmeter here to measure. That's all. That's a voltmeter.
Okay. But by putting the voltmeter there, it does complete the circuit, which would make it actually have a charge, right?
Yeah. So the current going here, nothing coming out. That's a voltmeter measuring.
Okay.
The current is negligible. Yeah.
Then I think how you would measure it is you would just take the measurement we just got, the 3.6 kilo ohms.
No. Now that's resistant. I forget about the circuit now. I want to find this one, and I got the original circuit, this one, and I drew it again. I just want to find the voltage here across EB.
Okay. In this scenario, would you? So you're ignoring the voltmeter. You're ignoring the other stuff.
Yeah, to make it simple, just you will say what is the voltage here, VEB, across the 9 kilo ohm. Let's make it
since now there's nothing, and nothing addition to it. Now it's a series circuit, which you would mean
Exactly, it's series, yes.
find the resistance, then find, well, actually,
What about voltage divider?
it's just, isn't it just 36?
No, because 36 will be divided among 6 kilo ohm and 9 kilo ohm. It will be 36 if I don't have resistance here. I have resistance here.
But you were asking for the voltage.
With the voltage across EB. Let me sketch again and then clean one. You got a resistance,
Yeah,
6 kilo ohm. You got a resistance, 9 kilo ohm. You got source, 36 voltage, and I'm asking what is the voltage across 9 kilo ohm? I think now it looks clear. Yeah.
okay, so the voltage across the 9 kilo ohm would have to be, hold on, I'm almost positive that there is a formula for this, but it's slipping my mind right now.
No, you don't have to have even a formula. If you have 36 volt and you got 6 kilo ohm and 9 kilo ohm connecting series, can you find the current? Yes. Current will be equal to 36
You can find the
voltage
current, yes.
divided
36,
by 6 plus 9.
which would be,
So it'll be
15.
36 divided by 15, which will be equal to 36 divided by 15, 2.4. 2.4 milliamp.
Okay,
All right. And now to find the voltage across 9 kilo ohm, which is AB. So VAB equal the current, 2.4 milliamp times 9 kilo ohm.
see, I was thinking about that and I was like, I was thinking about the difference between the voltage and the power. And I was thinking that power wasn't what you wanted because you had described that you wanted voltage across AB, but I forgot that if you find the power in milliamps, you can use it to find the voltage across resistance.
Oh, yes, you can, because you are multiplying milliamp by kilowatt. This is milliamp and that's kilo ohm. So it will cancel each other. When you multiply milli by kilo, they cancel each other. And there is another formula that is easy. You can get it directly called voltage divider. When you have connected two series, you want to find the voltage across 9 kilo ohm would be equal to the total voltage time the resistance you want to find the voltage across, which is 9, divided by the total resistance, which is 6 plus 9. That's the voltage divider formula. Which would be, it's also in I think in 100, EL 100. So that'd be 21.6 volt. So now we found the voltage source and we found what? The Thevenin resistance. So now the equivalent circuit, you have 21.6. Yes, V Thevenin, it's equal to VEB that I got. That's VEB. Let me write it here. Yeah, VEB. It's the same as, call it V Thevenin, just to honor the guy that we did it. And this resistance R Thevenin, we already found it in the first step, which is equal to 3.6 kilo ohm. 3.6 kilo ohm. And now I can connect the load that has diode. Where is the diode here, or the load? Well, the load is equal to diode and 1 kilo ohm. All right. So I put the diode and 1 kilo ohm. The question is now, how can you find everything? First, I want to know this diode will be on or off, and why?
It would be on.
On. Why?
Because there's current running through it.
How do you know the current running?
Because it's a completed circuit.
No, it can be also complete circuit, but doesn't work. It doesn't work. It got to be forward bias.
Yes, it's positive to negative.
Exactly. The positive is connected to V and the negative connected to N. So since it's ideal diode, be like a switch, I'm going to sketch the circuit again. I'll take the same circuit and replace the diode by the equivalent. This is the circuit that we just did. And since it's diode and on, I will remove the diode. And what I do, switch on. And now I can find the current. You have voltage, resistant, resistant. So the current in the load is equal to, let's call it IL, load current, is equal to 21.6 voltage divided by the total resistance, 3.6 plus 1, 21.6 divided by 4.6 kilo ohm. I get the answer in milliamp. 21.6 divided by 4.6 equal to 4.69. Okay, make it 4.7. Just round it, 4.7 milliamp. That's the current in the load. And if we want to find the voltage across this resistance, it's easy. The voltage across the load will be equal 4.7 times 1 kilo ohm will be 4.7 voltage. So the problem becomes easy when you use Thevenin, when you have a complex circuit. But this is ideal representation. And I didn't include the voltage drop or the barrier voltage, 0.7 volt. If you want to include it, what should you do?
Sorry, I missed that. What was that?
Okay, the diode that we represent, we said that it's either open switch or close switch. That's when it's on and that's when it's off.
Yeah.
That's when forward bias, that's when reverse bias. And we represent like switch, but and with the characteristics like we said that we represent like that. It starts conducting at V equals 0. But actually, there is a voltage barrier that's supposed to, if we look at the curve, we found out that it starts to conduct at 0.7 volt, not at 0. So if you want to include this voltage, what you should do, you should do something very simple. And you represent the diode by ideal diode like this, like a switch. And add a battery equal to 0.7 volt. So it's either open or close, and you have battery 0.7 volt. You just add battery in the opposite direction, 0.7 volt, opposing that. That's all.
So essentially, if there's power running through it, it should be closed and on?
Yes, it'll be closed, exactly. But there is a barrier voltage, 0.7 volt. It means if you have 0 volt, it will not work. You got to reach 0.7 to overcome.
Is that just a minimum of 0.7 volts, or is that a?
Yeah, this is exactly when the diode start to conduct. It conducts when you exceed 0.7 volt.
Okay.
But before
So
7 volt, yeah, because when you check the characteristic we just did,
it's
the
definitely
barrier,
over 0.7 volts.
yes. If you look at the characteristic, you see it will look like that, and that's the voltage across the diode, and this is the current. I will increase when there's 0, nothing, and once it start 0.7, start to conduct. So you have to apply voltage more than 0.7 volt, not 0 as the ideal one. Just put 0 and then 0.1, boom, will start to conduct now. So how we analyze something like that? Let me now give you a circuit and everybody is going to solve it. Now we have a diode, and I will write that has barrier voltage, I call it VT, is equal 0.7 volt. And I have a resistor. And let's say this resistance is equal to 2 kilo ohm. And I have a voltage supply across the diode. And the voltage, it looked like that. This is the time, and this is the voltage. And it was like -2 voltage. And then after 1 second, it jumped to 4 voltage. So I want you to think about it and tell me what is the value of current
Just current,
That's-
not current across the resistor.
current in the load. I want to find the current in the load I at T equal to 0.5 seconds, at T equal to, this is 1 second, at T equal to 1.5 seconds.
I believe it would be 4 volts.
Hmm?
Sorry. At T equals 1 second, or at T equals 0.5 seconds.
Yes,
is,
at 0.5 second and
0.5 seconds at negative, and then it's at the
yes,
-2.
yes,
and
from
then
0 to
at-
1 second is -2 voltage, and
At
after 1 second,
1.5, it is 4 volts.
yes. So I want to find the current at these 2 instants.
Okay.
Okay, I will give you how we still have on the class 10 minutes. Take the 10 minutes to solve it and give me the solution in a piece of paper.
How should I be giving you the solution?
You will scan it. After you do it, you scan it and send me email.
Okay.
Just send me my email. Yes. Yeah.
Using the fancy method of writing it down on a napkin.
No napkin. Because I mean,
Okay.
I don't have a good side. Okay, I will give you a chance to solve it, everybody. Okay, solve it and send it tonight to my email. That's good. All right. So you can okay, I'll dismiss. You can just take a break and go home and then think about it. It's easy, by the way, very easy. It's like one time you are going to apply -2 volt, and one time you're going to apply 4 volt. That's all.